Hi, I'm Manuel de la Pena. I am a staff software engineer at Docker. I'm the test containers Go maintainer, which is the library I'm going to present today. Our Go applications usually consume external resources, such as SQL or NoSQL databases, message queues for sending asynchronous messages, LDAP or mail servers, cloud services such as S3 or AWS Lambdas, and more recently, vector databases for AI applications. How do you make sure the application code interacting with those services is correct when you are writing it? Do you have the right tools to test your application while developing it so that you have confidence in creating the correct behaviors? One of the most adopted techniques is using a continuous integration server, such as Jenkins, GitLab Runners, or GitHub Actions, in which you or a platform team configures the servers to run all your dependencies in the CI pipeline. At some point, you must make sure that those dependencies, databases, queues, cloud emulators, etc., are in exactly the same version as in production, with the same configuration if possible. Also, the CI workers must be big enough to start and run those dependencies at the same time your test code is executing the test. My question is this kind of setup convenient for making progress? Every time you need to update the dependencies, you need to update the CI config, and many times, as a developer, you don't own the CI service. On the same hand, when your application grows and you depend on more services, you have to start them on the CI, increasing the probability of overloading the CI server with concurrent executions of different CI pipelines. Finally, how can you reproduce a failing test in your local machine in that scenario? Do you need to start the full-blown application to run just one failing test? Enter test containers for Go. Test containers is a set of open source libraries that are present in the most popular programming languages. I am the official maintainer for the Go implementation, and I'm going to show you how to use the library to resolve the issues I described before. First, Test Containers for Go gives you programmatic access to the Docker engine, so you are now able to create, start, stop, and terminate containers directly in your code. Instead of configuring the CI, you'll be adding the containers to the place they are used in your test code. Imagine you're working in the persistent layer. Instead of spinning up the entire application to run this layer's test, you just add an instance of your database where you really need it. So your test will interact with just a container representing that database. Test containers give you a random port for the well-known port for a given technology. For Postgres, it is the 5432 port. For MySQL, the 3306 port. This allows you to run multiple containers in parallel with three major benefits: consistency, test data isolation, and build speed. Consistency thanks to Docker containers. The dependency will be isolated in a container, so you don't need to mess up your system installing different technologies with multiple configurations that apply only to your host. Instead of creating an onboarding document with lots of instruction to set up the development or test environment, you just install Docker and run the test. We call it the clone and run experience. About data isolation, each container will have its own set of data. So depending on how you start them, by test function, by test suite, or by test package, you'll have more or less containers running in your system at a given time, but with no test data pollution. And for build speed, thanks to the containers, spinning up technologies as Docker images is a piece of cake. Of course, depending on the size of the image, you must pull it first, and it could be gigas. But talk is cheap. Let's show the code. We're going to present here a simple microservice app for rating conference talks. It provides an API to track the ratings of the talks in real time, storing the results in a Postgres database. Also using a Redis cache, a Red Panda as a broker for event streaming, and finally, it will use an AWS Lambda function to calculate some statistics about the ratings of the talk. We have an storage layer here with PostgreSQL in the talks repo.go file. So if we go to the talks repo.go file, we'll see the repository pattern holding the PGX connection. We build a new repository from the connection string, and with that we perform the CRUD operations: create, insert into SQL, exist with this SQL, etc. For the Redis cache, we follow the same pattern. We have a repository here, and this repository has a new repository receiving a connection string. We create the client, we ping the client, and we add find all, and we convert to a key here. About the streaming, we have here a broker, and this broker we define a client using the Kafka France Go package. We create a new stream from the connection string to the queue, and finally we do a ping here to verify the queue is up. And we're able to send ratings to the queue. To interact with the AWS Lambda, we have this Lambda client, which is basically doing HTTP requests to our URL. So we create the new Lambda client, basically HTTP client, with the Lambda URL as URL of the client. We're going to perform a post request to the URL of the Lambda. This is the expected response, and this is the payload that the Lambda will receive. Finally, we return the response so the application can consume the result from the AWS Lambda. How do we verify that those interactions work properly? The simplest way is to create integration tests with test containers Go. We're going to see them in action. For the Postgres database, we have a new repository test here, and we'll consume the Postgres module of test containers Go. We're going to create a container with all the options that we want to customize the Postgres instance, the SQL database that will populate the database, the name of the database, the credentials, and we are going to wait for the Postgres container until this log entry appears 2 times in the log. We're going to make sure the container is disposed at the end of the test. We're going to get the connection string to the Postgres instance, which is part of the API of the Postgres module. And finally, we're going to create our new repository, which is the persistent layer that talks to the database. If you recall, this repository received the connection string and performed the connections. Once we have the talks repository here, we're able to perform any CRUD operation, like creating, retrieving a talk, or checking it doesn't exist. We're going to execute this. We run the file test and see the logs here. We're going to see that test container will run the test and create the containers for us. Okay, it's using the Postgres 15 Alpine image. And in just 10 seconds, everything passes. Exactly the same for the Redis cache. We consume the module for Redis and create a container with the run function. We don't need to customize it here. We just consume the plain module. Again, we clean up the container. We get the connection string. We create a repository from the connection string. If you recall, it received the connection string. And once we have the repository ready, we are able to perform operations like adding on getting the results. If we run the test here, or Redis, we're going to see test containers running the Redis container and executing the test. In just 7 seconds, we are confident that our production code works as expected because it talks to a Redis instance. And finally, for the queue, we have this test. In our application, we are using Red Panda. For that reason, we are going to use the module for Red Panda in test containers Go. We call the run function from the Red Panda module with this Docker image, and we configure the Red Panda container to auto-create the topics. We calculate the seed broker URL for the Red Panda container, and we create our new string. If you recall, this string received the connection string and created the Kafka client. And we are able to execute our test against that Red Panda instance. We're going to run them. Probably it takes longer because it's going to pull the image. And finally, in 14 seconds, it is able to run the test against a real Red Panda instance. If we run the test again, we're going to see that it takes shorter time because the Red Panda image is already pulled. Just 5 seconds. Amazing. Let's see the code for the AWS Lambda. It is basically using the AWS Lambda Go package to create the Lambda, and it will receive this payload and will respond with this response. Here is handling the request, calculate the maths here, very simple. And finally, we have a main function, which is the start from the Lambda. Let's see how to test it. Here we are running make to ship the Lambda, which is basically packaging the Lambda into the artifact that AWS needs to create the Lambda. It's very basic. We see here that we are building the Lambda and creating a zip file for that, named function.zip. And for the test, we're going to use local stack. Local stack is emulating all the AWS services, specifically Lambda. And we're going to copy the zip file created by the makefile into the local stack container, and we are going to execute our custom code in the container after it starts in this case. We need to create the Lambda and get its URL. So for that reason, we're going to get the zip file here, create this Lambda command, which is Lambda create function URL config, wait for the Lambda to be ready, executing these commands inside the container, which is provided by test container to execute commands in the running container. Finally, we're going to get the function URL configs. And for that, we're going to pass the response. And we need the function URL here for the Lambda. This URL is the one needed to perform HTTP requests against the Lambda provided by local stack. So if we continue, we have now the container, we have the mapped port, we're going to replace this in the URL of the Lambda. This is needed because test container gives you a random port for the running container, for the well-known port for the running container. So we need to calculate that and replace it in the URL. We're going to pass this payload in our test. We calculate the histogram here. We perform a post request. And finally, this is the expected response from the Lambda. Pretty amazing, right? We're going to execute AWS Lambdas in our local machine. So we're going to run the test here, and we're going to see the local stack container running, where the code is calculating the URL of the Lambda. And finally, we'll execute the HTTP request against that URL. And the test pass. We're going to make it fail. For example, here, instead of calculating the average properly, we're going to introduce a bug here. And if we run the test, we are able to detect that bug. In just a few seconds, we are able to run locally AWS Lambdas and verify that our code is working as expected. Cool. We detected it. Total count is correct, but the average is incorrect. Where can I find more information about test containers for Go? If you visit the testcontainers.com website, you can find all the modules that we support for Test Containers Go. Here you can find for cloud databases, regional databases, NoSQL databases, vector databases, major brokers, web emulators, cloud, etc. A lot of them. All the modules are based on the container request struct. With this struct, you are able to configure your container as the way you want. For example, defining the image, defining the expose port, defining the network this container belongs to, defining the conditions to wait for this container to be ready, and more. For example, one advanced capability are the lifecycle hooks. You can execute your own code directly into the container lifecycle. For example, before the container creates, after the container creates, before the container starts and after it starts, before the container and after the container stops, before the container is ready, checking the health checks, and also before and after the container terminates. You can inject your own code and execute it in your test code. You can also create data into the container, for example, mounting volumes or copying files into the container. It's interesting that the files attributes allow you to copy container before the container is started. They are copied after the container is created, so when the container starts, the data, the state of the container is already there. This is really useful for containers with depends on a state. For example, databases. You can pass here a file to a SQL file to load the database, so the tests start with a well-known state. One interesting capability of test containers is Ryuk. You have probably seen the name Ryuk in the list of containers that are running in your system. This Ryuk container is responsible for removing containers, networks, volumes, and images created by test containers for Go, so you don't need to clean up the containers you create in your tests. Regarding the wait strategies, which I mentioned before, there are situations where you have to wait for the container to be in a well-known state. Instead of adding time slips to your CI pipeline or to your text execution, you rely on wait strategies. You wait for a command to be executed in a container, for example, like this. Here, let's wait for this command to be executed in the container. Or, for example, we can wait for a container to exit. At the same time, we can wait for a file to be present in a container, and the test will continue after this file is present in the container. Also, you can wait for a health check, waiting for the health check of the container. You can wait for a port to be already listening in your container, or an HTTP request, and you can configure the port you want to wait for, or even the path, the credential with basic auth, or even expecting a response code to be present in the response. You can also configure the response headers and wait for them to be present in the response. Another wait condition that is very handy is waiting for a log to be present in the log of the container. You can configure it to expect a string or a regular expression using as regex. You can also combine multiple of them with wait for all, and all of them will be applied at the same time. And you can wait for a SQL query to be executed on a database. It's also possible to use Test Containers Go for building Docker images from a Dockerfile. If you define this struct inside the container request struct, you will be able to build this echo Dockerfile in this path and with this repository name and tag name. You can also pass arguments to the build, and at the end the container will be running after the build. This is what I have. Here I'm sharing with you the QR codes to a Go workshop where we demonstrate the power of test containers for Go, and also the website with all the information about the project. I hope you enjoyed my talk. Thank you very much.